Okay, so today we'll journey from the quantum dance of light to the engineering marvels that bring us face to face with the cosmos, the telescopes. The topics that we will cover today are properties of light, the history of telescopes, classification of these telescopes, image quality, digital imaging using telescopes, and space telescopes. Before we build telescopes, we must understand their language. Light waves particle duality isn't just a theory, it's the reason we need different telescopes for different wavelengths and why we can detect stars billions of light years away. In 1801, Thomas Young performed an experiment so elegant it changed physics forever. By shining light through two slits, he saw the interference pattern on the screen. These alternating bands are the signature of waves. Where crests meet, we get brightness, and where crests meet trough, we get darkness. James Clerk Maxwell later proved light is an electromagnetic wave traveling at 3 to 10 power 8 meter per second, fast enough to circle Earth 7 times in a second. The wave nature explains why stars twinkle and why even our best telescopes have fundamental limits. Now let's see a video on the wave-particle duality.
You may have heard that light can act like a particle and like a wave. It can bounce off a mirror like a particle, and it can bend and spread out like a wave. For instance, when it passes through a prism. With careful experiments, we can see how light waves can interfere with each other. But did you know that particles can act as waves too? This is one of the central ideas in quantum mechanics. Everything has a wave nature. Light, particles, and even, in an unobservable way, macroscopic objects like baseballs and people. One way to see the wave nature of light is through diffraction, the way that light bends around the sharp edges of objects or creates patterns when passing through narrow gaps. In the double slit experiment, laser light passes through two slits in a wall and spreads out like a wave as it passes through. The waves coming from each slit interfere with each other, creating a pattern of light and dark spots on a wall on the other side. This happens because when two crests or two troughs of a wave meet, they add together, but when a crest and a trough meet, they cancel out. But what if instead of laser light, you throw particles at the wall? If you have a powerful electron beam, you can see that instead of two spots directly behind the slits, or randomly distributed spots, an interference pattern will appear, just like with the light. The electrons are behaving like waves and interfering with each other. Even weirder, you can slow the experiment down and send one electron at a time. Each electron will pass through and hit the wall at a single point. But over time, you'll see that the same interference pattern appears, even though no other electrons were passing through at the time to create interference. Apparently, each electron is actually interfering with itself. This is the crux of wave-particle duality. Even something we think of as an individual object, like an electron, has an essential wave-like nature and acts as a wave when it's moving through space. On the quantum scale, though, for very small particles, that essential waviness fundamentally changes how particles interact with each other, and it means we have to develop new ways to think about and work with the subatomic world. And in some cases, particles acting like waves can change the face of the cosmos itself.
All particles have a wave nature, which is super convenient for me because the particle that I study is super, super small. If you can try to envision how much smaller an electron is than a baseball, my particle is that much smaller than an electron. This means that its wave is huge, enormous, on the size of galaxies. So it's something that would actually be visible. And that's exactly what I study in my simulations of fuzzy dark matter, which is one possible explanation of dark matter, this mystery of missing mass in our universe.
Wave-particle duality applies to everything. If you like, you can even calculate the wavelength of a fastball, but it'll be much smaller than a proton, not nearly enough to blame for a strikeout.
Following this, we will study about the particle paradox. This was explained by Einstein in 1905. He explained that light arrives in energy packets called photons, and each color carries different amount of energy. The UV photons have enough punch to knock electrons loose, while red photons don't. This particle behavior is why modern detectors can count individual photons from galaxies billions of light years away. Next, let's learn about the EM spectrum. The EM spectrum ranges from gamma rays, which have wavelength of 10 to the power minus 12 meter, to radio waves, which have wavelength approximately of 10 to the power 4 meter. All of these wavelengths travel with the same speed, which is 3 to 10 power 8 in vacuum. They only differ in frequency and energy. There are various applications of these wavelengths of lights. The sources of gamma rays is from nuclear decay or black holes, and they're used in cancer treatment. X-rays can penetrate soft tissues, and it is used in taking the X-rays of bones. The ultraviolet rays are usually causing the ozone layer depletion currently all over the world. The visible light is the light that we can see and our eyes can detect. The infrared rays is used for thermal imaging. The James Webb Telescope uses this and is able to observe dust-shrouded star nurseries. The microwaves are used in radars and Wi-Fi, and radio waves are used, as we all know, in transmission of signals. Our eyes can just see 0.003% of the cosmic symphony. Now let's meet how the telescopes are able to capture the other wavelengths of light. The optical telescopes, as the name suggests, they capture the optical wavelengths, which can be seen by us. These use either lens or mirrors to focus the visible light, and they have CCD detectors to convert light into electric signals. The radio telescopes, they are used for capturing longer wavelengths than visible light, and they have a large parabolic dish like this as the antenna. They convert the radio waves into electric signals. The dish size determines the sensitivity and the resolution. The infrared telescopes, they use cooled optics or detectors which are sensitive to infrared radiation, and this is done to minimize thermal interference. X-rays or gamma ray telescopes, they require grazing incidence mirrors or specialized detectors because of the high energy the rays carry. Now let's compare these telescope designs. The radio dishes are large enough to hold baseball stadiums. The optical mirrors in X-rays are polished to atomic level smoothness for grazing incidence. Now let's learn about the functioning of telescopes. The telescopes have the light gathering part, which is basically the aperture of the telescope. A small aperture is used for capturing a less amount of light, and large aperture is used for focusing large amount of light. After this, we have the focusing. For focusing, we use either mirrors or lenses. Mirrors are perfectly curved like satellite dish so that there is no color distortion. Smaller focal lengths are used for wide views like of nebulas and galaxies, whereas long focal lengths are used for zooming into the Saturn rings. Following this, we have the detection, which is done by the eyepiece. The eyepieces are used for real-time viewing, whereas we can also use digital sensors like CCDs, which can be used for converting these light signals into electric signals for digital imaging. Following this, Janvi will take up.
I want to start it with a quotation. Edwin Hubble once said, "Equipped with his five senses, man explores the universe around him and calls the adventure science." And that adventure, it became a lot more exciting once we began building machines to see the unseeable. So let me take you through a quick journey through the history of telescopes. Let's rewind to 1609. Galileo Galilei didn't invent the telescope, but he was the first one to point it at the sky. Imagine this, that you're in Italy and you build a spyglass. You look up and suddenly you see Jupiter's moons, craters and the moon, or craters of the moon and even sunspots. Galileo's telescope magnified just 20 times, but it magnified our curiosity 1,000 times more. Here you can see a picture of Galileo's 1609 telescope and the observations and collection he made of the moon surfaces. Next up is Sir Isaac Newton. He didn't just give us gravity, he fixed a major telescope problem called the chromatic aberration. It means spreading out the wavelengths of different colors of an image. So you can't see a specific or precise image, rather you see a blurred and color being divided image as you can see in this picture. What was his solution? A reflecting telescope, using mirrors instead of lenses, more compact, less colorful mess and more powerful. Newton built it using a pocket knife, polished the mirror himself and made a telescope just 15 centimeters long. You can see the original telescope of Newton which he used for the observations. This design of reflecting telescope is the basis of almost all modern big telescope. You can see an example of Keck telescope here. Since then, telescopes kept getting better, larger mirrors, precise lenses, and more imagination. In 18th century, William Herschel discovered Uranus using these reflecting telescopes, and in 20th century, Edwin Hubble proved the universe is expanding, and all those inventions became very interesting. Now here's where it gets spicy. Spectroscopy. Imagine turning starlight into a barcode kind of thing, where each color tells you something about the star's temperature, composition, and velocity, and many more factors. Without touching a star, spectroscopy tells us what it's made of. Here you can see an example of spectra of the stars and nebulae. You can see how it's correlated to like barcodes and all. It was a very major discovery. But Earth's atmosphere is like a clingy friend. It protects you, but also blocks some cool things. So it blocks a view from the Earth. Ever notice stars twinkling? That's atmosphere basically messing with light. Some wavelengths like X-rays, gamma rays, and parts of infrared don't even reach the ground. So that's why we needed a better solution for this. So then came a revolutionary moment in astronomy. We said, why not take the telescope to space? And that's when Hubble happened. It was launched by NASA in 1990. The Hubble Space Telescope orbits just above the atmosphere, giving us crystal clear images free from Earth's turbulent atmosphere and all. Think of Hubble like the telescope that made universe look so iconic. And it's been working for over 3 decades. It was even serviced in space by astronauts during shuttle missions. So it had to be done hardcore maintenance and all. Now imagine taking Hubble's legacy, adding gold, origami, and super cool tech and all, and launching it far beyond the moon. So that is James Webb Space Telescope. I guess everyone knows about it. Launched in December 2021, it's not just a telescope, it's kind of time machine peeking into the past. It has infrared vision, a huge 6.5-meter golden mirror, 5-layer tennis court sized sun shield located at Lagrange point 2 between Earth and the moon. Now, with James Webb Telescope, we can now peek inside star-forming regions, analyze exoplanet atmospheres for signs of life, and observe galactic collisions. Now, I want you to show you a video of the movement.
Every image is a new discovery, and each will give humanity a view of the universe that we've never seen before.
This image, as we're looking at it, what we're seeing is not just all the galaxies, but there's a cluster here. And, it's really, there's so much detail here. We're seeing these galaxies in a way that we've never been able to see before.
These images are going to remind the world that America can do big things, and remind the American people, especially our children, that there's nothing beyond our capacity, nothing beyond our capacity.
Today represents an exciting new chapter in the exploration of our universe. This telescope is one of humanity's great engineering achievements.
This stunning vista of the cosmic cliffs of the Carina Nebula reveals new details about this vast stellar nursery. First of all, of hundreds of new stars that we've never seen before. We see examples of bubbles and cavities and jets that are being blown out by these newborn stars.
See lots of individual stars in there actually resolved as point sources, which is remarkable. Then as we pan across, we actually see the galaxies in the merging galaxies. We now see gas and dust, which is being heated up in the collision between those galaxies.
What you're seeing here is the telltale signature, the chemical fingerprint of water vapor in these atmospheres. There's evidence of clouds and hazes because the water features are not quite as large as we predicted.
Now that we have peeked into space with giants like Hubble and James Webb, let's look into the tools themselves, like telescopes. What are they made up of? Telescopes may look like just big tubes, but they come in all shapes, mirrors, and lenses. So how do you classify a telescope? Based on how it bends and reflects light. So let's explore the common types. Let's start with the basic one, the refractor telescopes. These use lenses to bend or refract light and bring it to a focus. You know those pirate spyglasses? That's basically a mini refractor, and we have extended them to make observations of space. The largest refracting telescope in the world is at Yerkes Observatory in US. Its main lens is over 1 meter wide, but it's also over 100 years old. The largest refracting telescope is in US, the Yerkes Observatory. Refractors are great for viewing the moon and planets, but they get bulky and heavy quickly due to long lenses maybe, and they suffer from a rainbow blur called chromatic aberration. We saw how Newton solved this problem. So now comes the game changer, that is reflector telescopes. These use mirrors instead of lenses. And yes, this was Newton's idea, to solve the color blur issue in the refractors. Instead of bending light, they bounce it off a curved mirror, and that was very powerful. Most of the big professional telescopes today, including James Webb Space Telescope, are reflectors. They're easier to make, larger, and are perfect for deep sky observations like galaxies, star clusters, etc. Now, what if you mix lenses and mirrors? You get compound telescopes like the Schmidt-Cassegrain or Maxtau-Cassegrain telescopes. These are compact, lightweight, portable, and amazing for both astronomy and astrophotography. Most of the telescopes you can buy as a hobbyist today are compound designs. So Kritika Observatory also features a Schmidt-Cassegrain telescope, the EDGE-HD11 telescope. So next time you see someone lugging a telescope to a stargazing event, it's probably one of these compound telescopes. I hope you'll attend the events. Remember those dishes in science museums that focus sound from one point to another. That's the power of parabola. It focuses to the focus of the parabola, and it works for light too. So parabolic telescopes use mirrors shaped like paraboloid to focus all incoming light to a single point, removing the spherical aberration also. So it's basically reflecting telescopes, but using a parabolic mirror. Most radio telescopes, including the massive Arecibo and FAST in China, are parabolic reflectors. So even if it doesn't look like a telescope, it can still be one.
This Chinese telescope is so big it can hear signals from the other side of the galaxy. It's called FAST, the 500-meter aperture spherical telescope, and it's not just big, it's the largest radio telescope in the world. Built deep in the mountains of Guizhou province, China, FAST sits inside a giant natural crater, far away from any human-made radio noise. It took over 5 years to build, with thousands of engineers working on it, and its dish is 500 meters wide. That's bigger than 30 football fields combined. In 2020, FAST heard a strange repeating signal, like a heartbeat in space. Some say it's noise, others say someone's trying to contact us. Is FAST hearing the first whispers from intelligent life? Or is something bigger going on in deep space?
Yeah. Now, here's a rare one, the elliptical telescopes. They are used in especially X-ray astronomy because X-rays pass through normal mirrors like a ghost, like you can't detect them from normal mirrors. So instead, these telescopes use grazing incidence, elliptical mirrors to gently reflect the rays. The whole structure and all is complex, but you can basically understand they make up ellipsoid mirrors, and the grazing incidence occurs through the light, and that makes us to detect the X-rays. NASA's Chandra X-ray Observatory uses this design, and it lets us see black holes, supernova remnants, and pulsars. It's like building a mirror maze for X-rays. You can see here 4 nested hyperboloids and 4 nested paraboloids in the cross section. These basically form a kind of ellipsoid type of structure, which makes the grazing incidence possible. Now, each telescope type is a different type. So we have built our telescope, chosen our mirrors or lenses, or picked our favorite type. But how do you point it at the sky? And more importantly, how do you make it follow a star that keeps moving all night long? So that's where these mounts come in. It's very useful and important for telescope. Think of mounts as the tripods with superpowers. They don't just hold your telescope steady, they help it track the universe. First up is the azimuthal mount, also called alt-az. These move in 2 basic directions: azimuth, the left-right direction; altitude, the up-down direction. It's like a camera tripod. You can swing it around and tilt it up. It's simple, it's intuitive, and it's perfect for beginners. So you can look at this 3D animation. It shows how an alt-azimuth mount works. In order for the telescope to track the movement of a star in the sky, it has to be rotated on the 2 axes represented with the red lines here. Next come the Dobsonian telescopes, one of the most loved amateur scopes, uses a chained azimuth mount. They are great for quick views of the moon, planets, and casual sky scanning and all. But if you want to do astrophotography or follow a star for hours, this mount might give you a lot of workout. So now let's level up. The equatorial mount. This is a masterpiece. It aligns with the Earth's axis of rotation, so you only need to rotate around one axis to follow a star across the sky. That axis is pointed to Polaris or celestial pole. You can see the red color line here. Imagine you're compensating for Earth's spin, and that's exactly what these mounts do. Now look at this 3D animation. This shows how an equatorial mount works. In order for the telescope to track the movement of a star in the sky, it only needs to be rotated on one axis represented with the red line. So it's more simple. Most observatory-grade and astrophotography setups use equatorial mounts. They even have clock drives that rotate the telescope in sync with the stars perfectly. Kritika Observatory has the CQ350 mount, which is also an equatorial mount, in a relatively modest 33 lbs, but also supporting a 77 lb payload capacity. This mount is what they call a portable beast. It's great for astrophotography, so you're welcome to see them at stargazing sessions or, yeah. And to take us into a world of pixels and starlit snapshots, let me hand it over to Sanvi.
Okay, so now we will study about image quality. We have seen many times how the light spreads across the corners of the object. That is basically diffraction, the light's stubborn habit of bending around edges. This is the enemy number 1 for astronomers. The bigger we build a telescope, the more we can fight this effect. Let me put this into perspective. The Hubble telescope with its 2.4 meter mirror can distinguish 2 fireflies 10 feet apart from 1,000 miles away. That's the power of beating diffraction with big aperture. Now let's study about the different effects and what are the parameters that affect image quality. The first is plate scale. The angular size of the object divided by the unit distance on the detector gives us the plate scale. A small plate scale implies longer focal length, which is used for higher magnification. This is used for planetary observation. A larger plate scale, on the other hand, involves shorter focal length and is used for wilder field view, which, for example, using deep sky imaging and for viewing galaxies. If you want to study the craters on the moon, you will need a small plate scale, whereas if you want to capture the entire Milky Way, you have to go big. After this, we have the focal ratio. The F ratio is the ratio of the focal length to the aperture of the telescope. It has the values like f by 4 or f by 10. Low focal ratio, which is f by 4 supposedly, is used for brighter images and gives shallow depth of focus. This is ideal for astrophotography. A higher focal ratio is ideal for planetary observation. We use higher f ratio because the planets are super bright, and this is a compromise for aperture that can be made. That's why deep space photographers love fast telescopes, but planetary scientists, they'll take slower f by 10 any day. Their targets are already bright enough. After this, we have the aperture. Aperture is the diameter of the primary lens or mirror used in the telescope. Larger aperture implies more light gathering and which gives brighter images and resolution. For example, the 10.4 meter Grand Canarias telescope, which is the largest optical telescope. Here's the golden rule. Double your aperture diameter and you'll quadruple the light. Now let's study about chromatic aberrations and the different type of defects that we get by using lenses and mirrors. The precision of optics of lens mirrors can affect the sharpness, contrast, and aberrations. Chromatic aberration is caused due to the difference in the refractive power of lenses to various wavelengths of light. This leads to color fringing, for example, the purple halos that we get around the stars. The solution for this is using achromatic lenses, supposedly using two different types of lens glasses like crown and flint to align the colors, or using reflectors like mirrors to avoid this completely. After this, we have spherical aberration. This is the blurring due to imperfect curvature, and it can be corrected using parabolic mirrors. Another type of aberration is coma aberration, or simply coma. This is the optical defect that causes off-axis point sources like stars to appear distorted, resembling a comet with a tail. This occurs because different zones of lens or mirror refract lights in varying angles, resulting in a non-uniform magnification. Now, what is the problems with using mirrors? Large mirrors gives us more light and better resolution, but are much heavier and costly. After this, we have spider vanes. Spider vanes are the support structures which are used for secondary mirrors that can cause diffraction spikes. These are usually thinner and curved to reduce spikes. However, it gives 2 vanes, 3 vanes, or 4 vanes appearance to stars. After this, we'll take up digital imaging. And this is the glass plate which was used for a century to record the universe. This captured only 3% of the incoming light. However, now we have these CCDs. This is basically a tiny silicon wafer which can capture almost 90% of the light. Now let's understand how these CCDs transform astronomy from fuzzy snapshots to precision science. How do these CCDs work? These CCDs have basically 3 major steps. First is the photon arrival. When the light hits a pixel, it frees electrons from that pixel. After this is the charge transfer. These electrons are then carefully passed along like a bucket brigade. And the digital conversion. Each bucket's water level basically gives us the pixel's brightness. CCDs count every single photon with military precision. An example of this is the Hubble Deep Field, the iconic image of thousands of galaxies. This was built from photons counted one by one over 140 hours. Now, why do astronomers love CCDs? First is the quantum efficiency. Quantum efficiency, or QE, is basically how effectively a device converts incident photons into charge carriers such as electrons. The quantum efficiency of CCDs is 90% compared to the film, which was only 3%. Then is the linear response. Double the light, exact double the signal, which means that the magnification of the brightness is directly proportional to our incoming light. These CCDs also have very low noise. They are cooled to almost minus 100 degrees Celsius, and they can detect objects 10 billion times fainter than visible to the naked eye. These are literally frozen to stop the atoms from wiggling and creating false signals. Now let's learn how do we convert raw data into cosmic portraits. First, we have calibration. Calibration removes any cosmic ray that show before or after the actual image. Stacking is basically combining 100 exposures of the image that we have taken to reveal the hidden galaxies. Colorizing, this is basically assigning invisible infrared to visible colors so that we can map them to the actual galaxies that we see. For example, this is used in the James Webb Telescope. The modern astronomy is equal parts of physics and photoshopping. Now, Jani will take up the space telescopes.
Yeah. So from blurred points of light to high-resolution galaxy portraits, it's amazing how far we have come in imaging. But What if I told you there's a way to go get even sharper, even deeper images by leaving Earth entirely? So here's where enters the space telescopes. These are ultimate dream machines because Earth's atmosphere, as wonderful as it might be for breathing, it is a kind of pain when it comes to astronomy and recording data related to the astronomy. So let's roll back to the mid 20th century, where astronomers knew that the atmosphere blocks large part of the electromagnetic spectrum. X-rays are blocked, ultraviolet radiations are mostly blocked, infrared are absorbed by the water vapor. And then there's the turbulence, it makes stars twinkle, which is pretty but terrible for astronomy. So the idea of putting a telescope in space became a mission to unlock parts of the universe which is invisible from the ground. So let's look at key advantages of space telescopes. There is no atmosphere in space, so there is no distortion. There is full spectrum access, the X-ray, UV, IR, even the optical range. There is constant observing, there is no day or night cycles, and it's better resolution and has longer exposures. So who wins, space or ground? So let's see a comparison between space telescopes and ground telescopes. So there is no atmospheric distortion in space, whereas in ground there is. In space telescope, there is full spectrum access, but it's limited in ground telescopes. The maintenance is difficult or in some cases impossible for space telescopes, but it's possible for ground telescopes. The cost is super high for space telescopes, and for ground telescopes, it's relatively lower. And when you compare sizes, space telescope is limited by its launch, whereas ground telescopes can be built huge ones, as we have seen an example in China, the radio telescope FAST. So both have their pros and cons. That's why modern astronomy combines both ground telescopes and space telescopes like Chandra and James Webb. So they work together to give us a 360-degree view of the cosmos. I want to show you some examples of space or ground telescopes. VLT, or the full form is Very Large Telescope. It's located in Chile in Atacama Desert. It's actually called the Very Large Telescope. And when they made another one, they called it Extremely Large Telescope. I guess they ran out of names. So these extremely large telescopes mirror will be 39 meters across. That's bigger than some of the planetariums. Now here comes another one. Why let mountains or earth stop you when you can fly? So here comes the SOFIA, the flying telescope. It's mounted on a Boeing 747. SOFIA was an infrared telescope strapped to a Boeing 747, flying above 99% of Earth's water vapor. Now, it had a garage-sized door that opened mid-air, so telescope could observe space while cruising at 40,000 feet. SOFIA retired in 2022, but it was the coolest observatories in the skies. Now, how do these SOFIAs stabilize? First, it isolates the telescope from airplane by mounting it on a spherical pressurized oil bearing. And second, it directs the wind away from telescope by shaping the side of the airplane so as to deflect it. And thirdly, it stabilizes the telescope against sudden motion by spinning 3 gyroscopes. So it was able to collect the data from the space. Next, coming to some famous space telescopes, let's begin with the legend Hubble. It's named after Edwin Hubble. This telescope orbits about 550 kilometers above Earth and has been taking photos for more than 30 years. It was launched in 1990. It's operated by NASA, the American Space Agency, and ESA, the European Space Agency. The instrumentation of Hubble include a wide field camera, VFC3. It's used for epic galaxy image collections. And next, cosmic origin spectrograph for UV studies. And there is an advanced camera for surveys. And there are some near-infrared camera and multi-object spectrometer, in short form, NICMOS. So Hubble's scientific instruments analyze different types of light, ranging from UV to infrared. This graphic shows which wavelength each instrument studies. You can see STIs and ACS and WFC3 and NICMOS, ranging from infrared and UV and even in the visible range. So now approximately 10,000 galaxies fill a small area of sky called the Hubble Ultra Deep Field. It's created through the collaboration of 20 astronomers and scientists. This is the deepest image of universe ever made at optical and near-infrared wavelengths. You can see how magnificent it is to see. Next, the Hubble Space Telescope is equipped to take images in various wavelengths, as we have seen, in order to provide more insights its targets. The famous pillars of creation in the Eagle Nebulae, also called M16, were imaged using both visible, you can see on the right, actually left, and the infrared, you can see on the right, different filters, the visible and infrared filters. Using infrared, Hubble is able to probe past the dense gas and dust of the nebula to reveal stars that are hidden in visible wavelengths. So you can see the comparison here. Next is, this Hubble Space Telescope image of star V838 reveals dramatic changes in the illumination of surrounding dusty cloud structures. This effect, called a light echo, unveiled never before seen dust patterns when the star suddenly brightened for several weeks in early 2002. And other major achievements of Hubble include Hubble has made over 1.6 million observations since its launch in 1990. There are more than 21,000 published scientific papers using Hubble data. Hubble transmits about 150 gigabits of raw science data to Earth every week. Over 25,000 astronomers have written science papers based on Hubble data. It proved the expanding universe theory. It measured the Hubble constant. It showed us stunning views of nebulae like the pillars of creation. It helped us to measure the age of the universe around 13.8 billion years. It captured the light of galaxies billions of years away. It discovered the accelerating expansion of universe and many more theories and cool theories. So Hubble literally redefined how we understand the cosmos. But there was a mistake. Hubble had a blurry vision at launch. It needed a kind of glasses. A servicing mission in 1993 fixed its optics. So the fix was nicknamed the contact lens of the universe. Now, let's look at another space telescope, the Chandra X-ray Observatory. Chandra doesn't look at light. It looks at X-rays, revealing the most violent events in the universe. It orbits a third of the way to the moon to avoid Earth's X-ray blocking atmosphere. It was launched in 1999 through the STS-93 shuttle in Columbia, and it's operated by NASA. The instrumentation is high-resolution cameras, HRCs, and advanced CCD imaging spectrometers called ACIS, among many other instruments. Now, this supernova is Cassiopeia A, the debris from an exploded star. So it gave us images of the supernova remnants, as you can see, the Cassiopeia A, and other achievements of Chandra include studied black hole jets in X-ray regions, helped discover the largest known shock waves in the universe. So Chandra also detected some sound waves in space, a B-flat tone emitted from a black hole in the Perseus galaxy cluster. Now let's look at a sonograph. So this was a sonograph of a jet emitted in the Perseus galaxy cluster. Now let's look at this golden time machine. James Webb Space Telescope is the most powerful space telescope ever built till now. It sees in infrared, allowing it to pierce through the dust and look into 13.5 billion years into the past. It was launched recently in 2021, and it stays at L2 point, 1.5 kilometers from Earth, and it's operated by NASA, the American Space Agency, the European Space Agency, and the Canadian Space Agency. The instruments of Webb, the major ones include the NIRCam, called Near Infrared Camera, MIRI, the Mid-Infrared Instrument, and NIRSPEC, the spectrograph, Near Infrared Spectrograph. FGS or NIRIS is Fine Guidance Sensor. You can see what's inside these, like you can see the classification of cameras, spectrographs, and coronagraphs. So what are coronagraphs? They are basically used for blocking the starlight, so that making the observation of planets nearby. So this is the first image of an exoplanet taken by James Webb Space Telescope. The HIP 65426 is about 6 to 8 times the mass of Jupiter and about 15 million to 20 million years old. And with Webb's ability to peer through cosmic dust, it captured stellar nurseries and individual stars in the Carina Nebula that were previously obscure. So one of the most striking images to come from Webb so far is the so-called cosmic eclipse, a cloud of gas and dust in the Carina Nebula, you can see here, located about 7,500 light years from Earth. Here, the cosmic cliffs are sonified or translated to sound. The blue gas and dust sound windy, while the melodic line represents the rise and fall of the mountain range. Louder tones represent brighter stars. So you can listen to it. So these sonographs are for blind or visually impaired people to get a glimpse of the space. So go look at them at NASA YouTube page, both from the Chandra X-ray Observatory and James Webb. They are so cool. Next, this image of galaxy cluster, the SMACS 0723, it covers a patch of sky about the size of a grain of sand held at arm's length by someone on the ground. So it's basically a very, very small portion of sky. It is the most detailed view so far of the early universe, revealing thousands of galaxies. So a cluster of galaxies located near 5 billion light years from Earth dominates this image. But the combined mass of this galaxy cluster acts like a gravitational lens, which you have gone through in previous modules, giving a magnified view of more distant galaxies in the background. So the lensing effect also creates so many curved arcs of light, which can be seen in this picture. Its very first image, SMACS0723, here's a comparison between the Hubble Space Telescope wala picture and the James Webb wala picture. So it showed us galaxies as they were over 13 billion years old. So you're looking at light that left those galaxies when Earth didn't even exist. So other achievements include discovery of carbon-based molecules in deep space, evidence of water vapor in exoplanets, so James Webb and many more. So James Webb is so precise, it can detect even a bee's heat signature from the moon. So it's basically a very important step taken by humanity. So there's a story. In 1995, astronomers pointed the Hubble Space Telescope at what seemed to be absolutely nothing, just a tiny dark patch of sky, smaller than the size of a grain of sand, and they waited for 10 days. What came back was the Hubble Deep Field, an image filled with over 10,000 galaxies, which you can see here. So in a spot where we thought there was nothing, the universe whispered you have no idea how much there is to see. So these incredible machines orbiting above us are not just hardware, they are kind of storytellers or carriers of messages of the universe. So every image they send back is kind of message. So thank you for joining us at Learner Space, presented by Kritika. Keep looking up and the universe is watching back.